Hello everyone. Let's continue our discussion on the CMOS inverter robustness. While we try to evaluate the inverter robustness of the CMOS, we need to consider one more point, and that's power supply scaling. So whenever you move from 250 nanometer node to lower nodes like 20 nanometers or so on, you scale your supply voltage as well. So for example, if things were working at 1 volt sometime back, now they will be operating at 700 millivolts or zero point 0.7 volts, or things that were operating at 2.5 volts like few years back, now things will be operating at 1 volt or 0.99 volt in that range. So we need to ensure that the CMOS inverter behaves the way it behaves under the power supply scaling scenario as well. So we have situations where we need to scale the power supply, let's say low voltage applications. In that case, the CMOS inverter behavior should not change, and that's the goal of this particular experiment that we are going to perform. So the experiment that we are going to do is some spice simulation. Okay, so we'll take one inverter. We have a PMOS which is bigger than NMOS, just to match up the resistances between PMOS and NMOS, and we talked about this in the past as well. And we kept the VDD or the supply voltage at as 2.5 volts. Okay, the PMOS width is 0.9375 microns. It's the NMOS width is 0.375 micron. The width of the PMOS is greater than NMOS because of the resistance effect. And then we will try to take the same PMOS and NMOS combination, or the same CMOS inverter as it is, and sweep the supply voltage from 2.5 volts to 1 volts, or maybe even 0.5 volts. We'll do the experiment for till 0.5 volts as well. Okay, so that's the experiment that we are trying to perform. And under this scenario, the goal is that the CMOS inverter behavior should not change. That's the goal, and that will eventually prove the inverter robustness. Okay, so that's what we are going to do. And there are a couple of ways that we can do some smart spice simulation. Okay, if you try to look into this particular scenario, there will be multiple spice netlists. One spice netlist for which the VDD is 2.5 volts, another spice netlist for which the VDD is 2 volts, and so on. Provided we sweep the supply voltage from 2.5 volts to 1 volts in steps of 0.5 volts, there will be multiple spice netlist. Or you can take up a single spice netlist, sweep the voltage from 2.5 to 1 volts in a single shot, and get all the curves the way you want it. Okay, so these are the curves for these are the plot that will be plotting for each and every supply voltage. For example, we'll draw a similar curve for 2.5 volts, for 2 volts, for 1.5, for 1 volts, and let's say for 0.5 volts. Okay, so I'll show you some smart spice simulations. Let me bring up the spice netlist. Okay, so this is the spice netlist that we were discussing in our course. This is the M1, PMOS, which has got the width of 0.937 micron, and of the technology node L equal to 250 nanometers or 0.25 micron. This is the NMOS. The M2 will be the NMOS, which is of 0.375 micron. Your PMOS is bigger than NMOS. Okay, the load capacitor we have kept as 10 femtofarads, is the same as the one which we did before. Your supply voltage, the initial supply voltage is 2.5 volts. Okay, the gate voltage will sweep from 0 to 2.5 volts. Okay, and then the first section of your spice netlist remains the same that we had before. The next section, which comes under the dot control section. So anything that comes between dot control and dot NC, you can do an amount of scripting. For example, you can do some amount of tickle scripting. So you can use some do while loops over here. You can set some variables and so on. So let me try to walk you through this particular set of script one by one. You first set the value of power supply, some variable. So power supply is the variable. Since just for the sake of simplicity, we use the variable name as power supply. So let the power supply be 2.5 volts. So let is very similar to a set which we have in tickle. So in tickle, if you want to set a variable, it's called set XYZ. In this case, in case of a spice behavior, it's let power supply. Okay, so the power supply variable we have set to 2.5 volts. Okay, and there is a construct in spice which says alter VDD equal to power supply. So in this case, alter will alter the value of VDD, alter the value of the default VDD. For example, in this case, the value of VDD was set to 2.5 volts. This will change the value of VDD to the variable power supply, and the power supply can be anything. In this case, it is 2.5 volts. But if I had put a 1 volt over here, the new value of VDD will be 1 volts over here, and the complete spice simulation will be run using VDD equal to 1 volt. Okay, and there is one more variable which is let power supply variation equal to 0. So we are setting another variable just to keep a track of the loop that we'll be doing over here. So let the voltage supply variation a variable will start from 0, and we will do the same simulation 5 times, basically whenever till this particular variable reaches a value of 5. We'll try to do this simulation. And the reason we are doing is we will sweep the voltage, we'll sweep the supply voltage VDD, which is 2.5 volts, in steps of 0.5 and bring it down to 0.5 volts. Okay, for example, 2.5 minus 0.5 gives you 2 volts, then 2 minus 0.5 will give you 1.5 volts, 1.5 minus 0.5 will give you 1 volt, and 1 minus 0.5 will give you 0.5 volts. So in steps of 0.5 we'll do 5 different steps, and in every step we will reduce the supply voltage, by 0.5 volts. Okay, and after setting the new power supply voltage by subtracting it from negative 0.5, by subtracting it from 0.5, we will alter the value of VDD on the fly and set the new power supply value to VDD. And so after this particular loop ends, the new loop, when it starts, it will first hit this particular line, and the DC simulation will be performed for the new power supply variation. Okay, so again the voltage power supply variation, we are incrementing it by 1 every time we enter the loop, just to hit this particular limit. And once this particular limit is hit, the SPICE simulation will come out of this particular do while loop and perform the next steps. Okay, so the next step is to plot the voltages. So in the past couple of videos we have been looking into SPICE simulation, where we do a set plot and we plot DC1, we set plot DC1, and then we plot out versus in. We have seen this in the past. In this case, since we know there will be 5 DC plots, we have given the name exclusively DC1, DC2, DC3, DC4 and DC5. Okay, and we have used the command plot DC1 dot out versus in. We have used the command plot DC2 out versus in, DC3 out versus in, and so on. So basically it's a different way to plot things in a single shot. Okay, and with that we will also put some labels. We'll put a X label which is called as input voltage, a Y label will be given as output voltage, and the name of this particular curve will be given as inverter DC characteristics as a function of supply voltage. Okay, so these are just to make things even more clear, to basically the documentation or so those kind of things are important while we script things in SPICE, just to make things in a more understandable format. So anything that comes between dot control and dot NC, those allow you to script things inside this one. So if you want to do some more complex simulations, you can just write the script over here, and then under the section dot control and dot NC, and there you go, you will be able to do some amount of complex scripting over here, some smart SPICE simulation. Okay, and the remaining of these simulation commands remains the same. So this we have commented because this is now, the simulation part is now a part of your do while loop itself. So we can comment that. And finally the last steps is to include the model file. Okay, so I have the SPICE simulator as well. Let me open up that. Okay, this is a SPICE simulator. So we'll first go to the area. So this is the area where I have kept my SPICE netlist. Okay, so we will cd to that area. Okay, we'll source the circuit file. Let's say the circuit file is this one, which I have given a name, scaling supply voltage. If you see over here, it's scaling supply voltage experiment. So I've given that particular name. So let's use that. Okay, we will source this, and the moment we source this, we'll see some SPICE simulation happening in the background and the curves available for us, and the reason is because we are plotting in the SPICE netlist itself. We are using the commands of plot in the SPICE netlist itself. Okay, so let's do that. And these are the curves. So these are the different curves for different voltages. For 2.5 volt power supply, this is the CMOS curve, which I think we have looked in the past also. This is the plot for the CMOS parameters. The width and the length of the CMOS parameters remains the same. Only the supply voltage changes, and this is the curve for that. And this is the curve for 1.5 VDD. This is the curve for 1 volt VDD, and this is the curve for 0.5 volt VDD. Okay, so there is very important conclusions that needs to be made out of this, and exactly we'll be doing the exact thing in the next couple of videos. So just an observation, if you see, even at 0.5 volts your CMOS is able to operate. Okay, so from the next video, what we'll do, we'll take this particular plot, we'll keep that as an agenda, and we'll try to analyze about this particular plot. We'll try to analyze what are the outcomes and what are the advantages and disadvantages of running your CMOS at a lower voltage. So let's try to do all this from the next video. Thank you.